What's up, y'all? We're here with a Codeforces contest. This is round 839. Here we go. You have to evaluate. Okay. Does that work? Should work. Okay. You can rotate it. Okay, sure. Don't have my usual keyboard today. Is this the right way to do this? I think it's just... one of them is strictly the minimum, one of them is a strict max. And then they're opposite. Alright, let's do this. It'll be a little weird, but... not... Okay, now we need to check strict minimum. Equals max index equals min index plus 2 mod 4. Opposite. I not equal min index and then it's false, and then same thing for max. Really? Oh. Wait, what? Wait, what? Oh, wait a second. This should not be no, yes. It should be yes, no. Okay. That's really bad. Oh, that took me a while. they have to be k integers from 1 to n. So wait, what? So yeah, there have to be two sequences. They have to have no overlap. Instantly at the beginning. I think you can't you just take the longest increasing sequence? And then find the oh, wait a second. I think we want to do this. Okay, so value is going to be AI, compare is going to be greater equal int. I think that's what we want. D. I mean, oh, that is important. This has to be 4. Okay, this is actually what I want. So I want to do this, and then I want to do Oh, I see. What? No. I'm doing this wrong. I don't know. Yeah, okay, so check some X and then okay, so what we got going on is we want AI minus X. What does that mean? That means X is closer to AI than AI plus 1. Oh, so each, okay, I'm doing this completely wrong. No. What? What is going on? Just give me what I want. Yeah, this is what I need to do the whole time. Okay, that's not. Oh, if they're the same, you don't do anything. Okay, I think we got it now. That was really bad. Very bad. Just terribly bad. Yeah, should have thought more before coding that. Okay, so strictly increasing, so. Oh yeah, there are just certain gaps that you. So the sum is. Yeah, you just fill the rest with ones. Okay, so. You get k minus 1 gaps, and then to sum to n moves to n minus 1. n minus k. That is not. Oh, extra minus. Oh, I should start gap at 0 because we don't want to do 1, 3 right away. 1, 2, 4. That seems good. That seems fine. Okay. I'm not anywhere near the top. Interesting. Change something to blue. Can move the. Okay, let's say it does become sorted at some point, then the red elements were already in the right place. And then the player just moved the blue things. Oh yeah. So they cannot. If you're like making progress, they can't stop you, but maybe they can do. Yeah, so a tie would happen if it's odd and. Wait, what? How is this a tie? 2, 3, 4, 5, 6. Oh, you want to make everything except that blue? Okay, there's things, yeah, there's things first one wants to make blue, there's things second wants to make blue, and there's things they both want to make blue. Would you ever shuffle that? That doesn't. No, you're just wasting a turn. Just they're already blue. It doesn't matter. So first one's. We see. So yeah, I think you just count how many. It's still a test case problem. Our first once is going to be pi not pi. I think basically yeah, okay. If first blue plus both blue else if second blue plus both blue is less than first blue. And I think that's it. Oh, I missed it. Okay, well. Second blue plus. Yeah, so yeah, this is right. Oof, this gap is just really bad. I have worse penalty than people with 6 problems. Not good. Oh, interesting. Interesting. I think you can sort them by. You just sort them by how many pairs of things are different or equal. And then you just need to like. Oh, then you need to. I just need to like. It's just annoying that you have to generate this sequence. It's just a bunch of implementation, basically. All right, sure, let's do it. It's gonna be vector, vector, vector. Nope, no, just vector, vector, actually. It's not too bad. All right, we're gonna return. Yeah, not the best keyboard for this. Okay, so let's do that. I think we should already have the right order. We just need to just set up a sequence. What is this? Yeah, so put the one in. We started with. Yeah, I mean, that works. So now, constructing a sequence. Yeah, I mean, we don't need to worry about time complexity, so. Oh no, come on. I have to do the index? That is really annoying. Okay, great. Now I don't have to worry about that. And then what happened? The index of the initial picture. All right, now let's do it. Find all the differences, and then four. Okay, yeah. Okay, so all right, return if r equals 0 or r equals minus 1 or c equals 0 or c. It's just this is just a bunch of much typing. All right, so if board equals next board, this is what, well, true, I guess. Then we did it. Break. Otherwise, well, that can just be the wild fish. If board RC not equal to next board RC and can change board RC, then do it. One equals 1, right? Yeah, that's it. And then I'll push back to find board next to board plus 1. I think that's it. We're just going to output vector. I only need to check the ladder two. Past. Really? Okay. Looking good. Well, I have horrible penalty, but I can solve the problems. So there's that. All right, G. Geothermal has already solved G. Okay. Okay. Interesting. Oh, really? You don't play I, you cannot play J. You always have to play someone who's tied for the min. See, don't you just sort them and then you just go in that order? You go 1, 2, 3, and now you're at 5, and then you play 5, right? Now you're at 6, and then you lose to these 3, and now you're at 3. And you do it again, so 7 and then 7. And then the next time you do it, you are actually going to beat this guy. And so you'll gain 3. Well, you'll stop in the middle because you'll be at 4, and then you'd be like 5, 6, 7, 8, 9, 10. And so you did 20. Yeah, you did 20. Okay, I see. Okay, so you're just gonna, this is another test case problem. Okay, so yeah, so because we did not succeed. If first run dot second 0, that's just an N. If first run dot first X, then you cannot, you're not making any progress. So this should solve the latter two cases already. And then now we know that a full run oh, we also need to know the peak, right? Well, the peak is just binary search. No, it's, well, definitely not. Oh wait, I can't even, well, N is big too. Okay, we can calculate this array need. So need I is just AI minus I. And then make sure it's sorted. And then now we know it's possible. We know it's possible. So all right, so actually, no, why are we doing that? This makes sense. Yep. So just while true. You know, this is like, let's just call it need count, I guess. That's how many were past the need. The phase length is going to be, it's just infinity. Otherwise, the gain is need count minus n minus need count. It's just, I should use seal div, this is better. Who uses floor div? Okay, that's how long we're in this phase. If it should be at least okay. So if x plus phase length minus 1 times gain plus need count is at least y, then you can finish it here. Times this. Yeah, y minus x minus need count divided by gain. That is how many rounds. do that many rounds. Oh, we also need to track of like current equals 0. Y minus x. Times n plus y minus x. That's it. That's actually it. There's no best, no need best. Oh, this is gross. Oh no. Okay, that's fine. All right, otherwise current plus equals phase length, x plus equals phase length times gain, and then you continue. That's it. That's it. That's it. I guess that's it. Two and 2. That sounds right to me. Let's try it. Why not? Okay, cool. Well, I'm still bad, but at least I finished. Yeah, that is really bad for ICPC because I took so long on these two. No wrong submits though, that's nice. Yeah. All right, let's save everything. And all right, let's talk about them. So first problem A, pretty simple one. You're just given an expression a plus b. They even give you single digits, which is nice. You need to evaluate it. I just took the values. You subtract out ASCII code for 0. Technically, this might be a little easier to understand, but then you just add them up. A trick you can probably do in like Python, but not C++, is you can do eval, which is not necessarily a safe thing to run, but in this case, because the problem just gives you these, additions, it'll just work. So, I guess we could. All right, let's try doing that just for fun. Pi. T is going to be int input. I forgot how this works. So I think this is fine. And then is it just that? So yeah, okay. So we can just submit this actually. What do I want to use? I guess Pi is the fastest. Not that it matters here. But yeah, okay. Well, that's pretty slow. 46 milliseconds to run this. Anyway, that's problem A. Really simple. Problem B. Oh yes. Oh, they're distinct. I didn't. Okay. So clearly I messed this up, but a matrix is beautiful if the two conditions are satisfied. In each row, the first element is smaller than the second, so 1 is smaller than 3, 5 is smaller than 7, and then in each column, the first is smaller than the second. So 1 is smaller than 5, and 3 is smaller than 7. So all this means is that the min value is here and the max value is here, actually. And because they're distinct, I don't need to worry about making sure that min and max are unique. Anyway, the other thing you can do is you can rotate it as many times as you want to try to get it to be beautiful. And you want to determine if it's beautiful after you apply some set of operations. So now, because you can rotate it any way you want, actually now all you want is that the min and the max are diagonally opposite each other. So it could be like min here and max here, and that's fine because you just rotate it, right? Or it could be min here, max here, and then you just rotate it twice, and then you're good. So that is what I implemented. You don't need to do any of this. You just delete this. And so I just flattened it. I made it an array of size 4. One tricky thing is you need to swap 2 and 3 so it actually has a circular order. But otherwise, this is all you have to do. I'm going to resubmit because, again, overcomplicated it, but that's not Python. Here we go. Cool. So that's problem B. Problem C, yes. So problem C, you want to make a strictly increasing array, and you want to have the maximum number of distinct consecutive differences in your array. So for example, when you have 1, 3, 4, 7, 8, the difference here is 2, the difference here is 1, difference here is 3, difference here is 1. So 1, 2, and 3 all showed up, so that would have a characteristic of 3. And you want to maximize that. But you need to make your array have k integers between 1 and n. So that's just a greedy problem. Basically, you just set up as many as possible, as many differences, and you just obviously use the differences 1, 2, 3 until you run out. So you need to make sure that you don't. The problem is if you try to do too many big differences, you won't be able to fit in 1 to n, right? And so basically what I do is I start with 1 as the beginning of my array. I know that the amount of kind of extra space I have is n minus k, because if k equals n, then the only thing you can do is 1, 2, 3 all the way to n. And then the bigger n is, for every one bigger n is, you have one more kind of breathing room. And then, yeah, I'm just trying to add a 1, trying to add a 2, 3, and so on, until I run out of that extra space. So while I still have the extra space, I add a new bigger gap, and then I fill it out. And then by the end, I just keep adding 1 to the remaining values, and that until I reach k values. And this is just like the safe way to finish out the array. So the key logic is here, where I'm calculating how much extra space I have. So for example, for 5, 9, I have kind of 4 extra space, because I could start with 1, 2, 3, 4, 5, and I could bump up numbers up, up to 4 times until I hit 9. And so in that case, I do 1, 2, and then I do 2, 4, and then I do 4, 7, and then I can't add another. So I do 1, 2, and then I do 2 to 4, which is plus 2, and then I do 4 to 7, which is plus 3, and I can't do plus 4 now because that would hit 11, which is way bigger than 9. So I just stop there, and then I just finish up. So that's C. Problem D. Yes, this problem I went down a rabbit hole that was not the right thing to do. But anyway, it's actually, you can kind of just tackle this very straightforwardly. So you're given an array, you want to make it sorted by applying this operation. And you pick x and you replace ai with absolute value of ai minus x. You want to find any value of x that'll make it sorted, or report that there's no such value. So did I make a, oh, I didn't save that. Okay, well, basically we just go ahead and directly say, this is what we want, right? ai plus 1 minus x. And this is the condition we want. If this is true for x for every I, then we're good. So what does this condition imply about x? Well, this just says that x is closer to ai than ai plus 1. Or at least as close. Okay, so does that give us some constraints on x? Well, if ai is less than ai plus 1, that gives us like a max value for x. For example, if ai is 3 and ai plus 1 is 7, that means x is at most 5, right? Because if x is bigger than 5, then it's closer to ai plus 1. And then similarly, if the order is reversed, you get something similar. It's just in the other direction. This time x is at least 5. One tricky case is if ai equals ai plus 1, then you don't actually have nothing, or you don't actually have anything. No constraint on x. So that's what we do here. We just track the minimum and maximum values for x. It's just a range. And if ai is less than ai plus 1, then you have a constraint on the max. If ai is greater than ai plus 1, you have a constraint on the min. If they're equal, you don't do anything. Again, that's important. And then at the end, if our range still exists, then we can print out an answer. Otherwise, we can print -1 for impossible. And it doesn't matter what we print. We can also have printed minimum here. That should also work just fine. We can submit it even. All right, so that was D. And then keep going. There was no H. Yeah, the rest of these I'll explain a little more quickly, but basically for this problem we have a game. You can turn elements of your permutation from red to blue, or you can move around all the blue things, or you can skip your turn. And the first guy wants to sort it 1 through n, the second guy wants to sort it n through 1. And it can also end in a draw. I want to figure out who wins. Well, basically, the first guy is going to figure out, basically you would never do this operation until you can just win, because essentially the red elements cannot move, but the blue elements can move anywhere. And if you move around the blue things but you do not win, you've basically just wasted a turn, because if you could win on a future turn, or your opponent could win on a future turn, then your shuffling the blue elements didn't do anything, because whatever you do, you can just replace it later, because nothing turns from blue to red. So everything that you moved will be movable later. So basically they're just going to be doing this operation or skipping until one person can win. And yeah, so basically we can just count how many elements the first person wants to make blue, as in it's not in the right position to be in 1 through n. We can count how many the second person wants to make blue, which is it's not in the right position for n through 1, and how many both of them want to make blue. And so that's what these counts are. First blue, second blue, both blue. And basically the first player wins if first blue plus both blue is less than or equal to second blue. What does that mean? That means that he can turn all of these values and all these values blue before the second player can finish these. And then he can do that operation and then win. And second player wins if second blue plus both blue is less than first blue. Notice that this is one stricter than this condition, and that's because second player goes second. So same idea. And then otherwise it's a tie, because what happens is they both like very frantically finish their own groups, and then they're left with only the both blue group. And no one wants to finish the both blue group, because then the other player would win on the very next turn. So they both will just, once they get to the last one, they'll just keep skipping the turn. And that's it. This is a pretty simple code. You just have to think through the game, and that's the logic. All right, so there's E. Let's look at F. Yes. So for F, you have a grid, and you can do this one operation where you choose a cell that's on the border, but it's surrounded by 4 cells of the opposite color, and you paint it that opposite color. or you can make a copy of your current picture. And you're given a bunch of the copies, and you need to work out what happened. But they're not necessarily in the right order. They could be shuffled. And so first we need to figure out what their order was, and then we actually need to reconstruct the sequence of events. So to figure out the order, well, we need to figure out some sort of way to sort them. It turns out, if you think about that operation, so, in this case, something like this. If you think about this operation, we're turning this 0 into a 1, right? And so what would tell us that we need to sort this later than this? Well, the thing I did is basically for every horizontal or vertical pair, I count how many of these pairs are equal. And when you do this operation, you're always increasing the number of pairs by 4. So it only goes up. And that just gives you a very clean way to sort them. So that's what I did. Just sort all these boards by their pair counts. That's what I did here. Notice that the constraints are super small, so I don't have to write time complexity, just do anything that works. So I take the boards, I sort them. This is a little bit of annoying logic to reconstruct the original index of the board. But this is the sort, this is the key idea. And then now I have to reconstruct the operations in between. Again, you don't have to be too super efficient. I just take the board and the next board, make a copy of both, and then I just iterate through and look for any operation that I can do where it actually did change. The problem is there's like potential ordering issues where well, are there? Maybe there aren't. Maybe I tricked myself. Actually, maybe there aren't. Maybe this just... Does this just work? This might just work. I don't even need that. Let's try it. Yep. Okay. There are no ordering issues. You just go through and you find the things. I don't even... Okay, that's really silly. I don't need this. I don't need this. I don't need any of this. I don't need this. See, if I just come up with all these things, I could have done all these problems much faster. But yeah, okay. You literally just find the locations where they're different and you just add them to your ops. It's actually very simple. And then yeah, I have this find board logic. Just iterate through the boards, find that board. It's a little tricky because you can have multiple copies of the same board, so you just need to make sure you don't use the same index again, and that's what this found array is for. But otherwise, you just kind of do it, and then you're good. Let's see, am I still in 5th? Probably not. Yeah, okay, there we go. Okay, and that was problem F, and now problem G. Yep. So problem G, Monocarp is trying to increase his rating. If he wins, which means he's greater than or equal to the other person's rating, his rating will increase by 1, otherwise it will decrease by 1. His opponent's ratings do not change. And he wants to go from X to Y by playing as few games as possible. But basically he always has to play against someone who he's played the minimum. So he's not allowed to play against someone if there's another opponent who he's played less against, which is very, very intense, very strict rule. But anyway, and notice that N can be pretty big and X and Y can be really big. So now we need to figure out, can we get to Y? If so, what is the fewest number of steps? And okay, so basically, if you just think about it, it's pretty clear that you need to sort the ratings, and you will just go through the ratings in order. Like you will play the lowest rated player and the next lowest and so on, and until you go through all of them, and then you'll just repeat. And that's kind of the only operation you can do. And so you could just simulate that, but that would be too slow. We need to be more efficient than that. So what we can realize is, first of all, we can notice Okay, when we do a run through, and this was a little silly, wasn't it? Yeah, I kind of like redid this logic later here, but that's all right. So what we can figure out is if we do a full run through all n opponents from smallest to largest, how does our rating change? So first of all, we could potentially finish right away before even doing a full run through. If that is the case, then we just output the answer. And then after we do the full run through, we need to see what our new rating is. If our rating did not increase, it's the same or lower, then it is not possible to get to y. Because every time we go through, it will not increase, or it'll even get worse, and we'll never get to a point where we can increase to y. Because we need to keep doing this run through. Otherwise, we know that we'll increase by a certain amount. We know we'll get there eventually, because if we just keep going through again and again and again, we will keep increasing our rating. And it can only get better as we start beating more opponents. But we need to do this efficiently because basically we need to simulate how our increase will increase because as our rating gets higher to start with before running through all the opponents, then we will actually beat more of them. And so we were kind of simulating those events. And so that's what I do here. I figure out how much rating you need to start with in order to beat a particular person. And then just repeat, figure out how many people we're beating when we run through now with our current rating. Figure out how much we gain by beating that many people. And then there's this thing called phase length. So this tells me how long do I, how many times do I need to run through the full set of opponents until I start beating at least one new opponent. And that's just some calculations, just some divisions. Basically, there's a lot of calculations in here. I won't get into all the details, but figure out how long until I beat an additional opponent. And then I figure out, okay, am I going to win in this phase? This is a little tricky because you would do phase length minus 1 full run-throughs, and then you would do only the prefix that you beat. And if that's the case, if we win in this, then we figure out how many run-throughs we actually need, and then output that. Otherwise, you go through the entire phase, just gain all of that, and then go to the next phase. Yeah, that's it. So that's all the problems. I guess I could clean this up potentially and just reuse that logic. Maybe I'll do that. All right, sure. So, oops. That's if we can finish immediately. That tells us if we can finish immediately. And then if gain is less than 0, then we're in trouble, and we can just quit. Yeah, I think that should do it. And we can just submit it again. Yep, looks good. Cool, so that simplifies the logic a bit. But yeah, that was it. Codeforces around 839. Looks like we're still holding up in 6th place. So, you go, wow, Rainboy actually did the whole contest. That never happens. Anyway, cool. Thanks for checking this out, and I'll see you in the next one.